From leveling down an entire city in seconds to causing genetic mutation of an entire race for decades, this is how a nuke works. When most people hear of a nuclear bomb, they immediately think of the tragic events of Hiroshima and Nagasaki, and well, they are not wrong. A nuke is a weapon that releases enormous amounts of energy by changing the structure of atomic nuclei. This energy is not chemical like gasoline burning. Rather, it is locked inside the heart of atoms and unleashed by nuclear reactions. The result is a blast of heat, pressure, and radiation that can destroy cities in an instant and leave lingering contamination for years. The story of nuclear weapons begins with the discovery of nuclear fission and fusion, processes that occur on a scale so small that they are invisible to the naked eye. Yet they are so powerful that they reshape geopolitics and human fears. How it works. Before anyone could understand how a bomb of such power could ever exist, scientists had to start from the tiniest building blocks of matter, the atom. Every atom is made of three smaller particles, with protons and neutrons sitting at the center in the nucleus, and electrons circling around them. Protons carry a positive charge, electrons carry a negative charge, and neutrons carry no charge at all. In a neutral atom, the number of protons and electrons match perfectly, such as in a carbon atom that has 6 protons balanced by 6 electrons. Yet atoms are not always that simple because their behavior depends heavily on how many of each particle they contain. If the number of protons changes, the atom becomes an entirely different element. But if the number of neutrons shifts, the atom simply becomes a different version of the same element, known as an isotope. Carbon provides a clear example of this, since it has 3 main isotopes: carbon-12 with 6 protons and 6 neutrons, carbon-13 with 6 protons and 7 neutrons, and carbon-14 with 6 protons and 8 neutrons. The first two are stable, but carbon-14 is unstable and radioactive, slowly breaking down by emitting energy in particles. Radioactivity comes in different forms, with alpha decay releasing 2 protons and 2 neutrons bound together, beta decay turning a neutron into a proton, an electron, and an antineutrino, and spontaneous fission splitting a nucleus into 2 pieces while sending out neutrons and powerful gamma rays. That last process, fission, becomes especially important in the story of nuclear bombs because it shows how splitting a single atom can trigger an enormous release of energy. The key to nuclear bombs lies in the forces that hold the nucleus together, because energy can be released in 2 ways. The first way, fission, involves splitting a heavy nucleus into smaller pieces using a neutron, while the second way, fusion, involves forcing smaller nuclei together to form something larger. This is how the sun produces its constant stream of energy. Both methods release huge amounts of heat and radiation, and both became the foundation of nuclear weapons. In the 1930s, Italian physicist Enrico Fermi showed that bombarding elements with neutrons could change them into new ones, and his work eventually led to the discovery of slow neutrons. A few years later, German scientists Otto Hahn and Fritz Strassmann found that when uranium was struck with neutrons, it split into smaller atoms like barium, releasing energy. This meant that uranium nuclei were capable of undergoing fission. Soon after, Niels Bohr and John Wheeler developed a model showing that it was uranium-235, not uranium-238, that was most responsible for this process. What made the discovery so remarkable was that fission not only released energy, but also produced additional neutrons, which could strike more uranium atoms and trigger a chain reaction. That idea opened the door to building a weapon that could release unprecedented amounts of energy. By 1940, researchers in New York confirmed that uranium-235 was indeed the isotope responsible for sustaining fission. Early attempts to start a chain reaction failed, but in December 1942, beneath the stands of the University of Chicago's Stagg Field, Fermi successfully oversaw the first controlled chain reaction. This milestone showed that a nuclear bomb was possible. Uranium-235 became a prime candidate for bomb fuel because it could capture neutrons and split almost instantly, releasing more neutrons and radiation. Each reaction happened in trillionths of a second, and if enough uranium-235 could be concentrated, the chain reaction would grow uncontrollably, releasing vast amounts of energy. The challenge was that natural uranium contains only a small fraction of uranium-235, so the isotope had to be enriched to more than 90% to reach weapons-grade levels. Around the same time, scientists also discovered another element, plutonium-239, which showed strong fission properties and soon became another option for bomb fuel. Designing the first fission bombs meant solving how to bring separate pieces of fissile material together quickly enough to create a supercritical mass. If the pieces stayed apart, no reaction would occur, but if they were forced together at the right moment, a runaway chain reaction would begin. The first method was the gun-type design, which fired one piece of uranium into another to form a supercritical mass, as in the Little Boy bomb dropped on Hiroshima. The second method was the implosion design, which surrounded plutonium with high explosives that compressed it inward, as in the Fat Man bomb dropped on Nagasaki. Implosion was more complex, but it allowed plutonium to be used efficiently, and it quickly became the preferred design. Even after these weapons were built, scientists kept improving them. Edward Teller introduced the idea of boosting, where small amounts of fusion fuel inside a fission bomb produced extra neutrons, increasing the efficiency and power of the explosion. Eventually, fusion itself became the focus for the next generation of weapons. Fusion bombs, or hydrogen bombs, worked on the opposite principle from fission, by forcing light nuclei together under extreme heat and pressure. The fuels of choice were deuterium and tritium, isotopes of hydrogen, which could fuse to release massive energy. Since storing these gases was difficult, scientists used lithium deuteride, a solid that could produce tritium during the explosion. The design of these bombs relied on a two-stage system where a fission bomb served as the trigger, producing X-rays that compressed and heated the fusion fuel. Inside such a device, the sequence unfolded in less than a billionth of a second. The fission stage imploded, releasing X-rays that heated the bomb's interior, compressing the fusion fuel 30 times its normal density. The conditions became hot enough to drive deuterium and tritium nuclei together, releasing more heat, radiation, and neutrons. These neutrons then caused the surrounding uranium tamper to undergo fission as well, multiplying the power of the explosion. The result was a blast many hundreds of times stronger than the bombs dropped on Japan, with yields measured in megatons rather than kilotons. What began with the simple splitting of an atom had evolved into weapons capable of reshaping entire landscapes and altering the balance of power across the world. Yet having a nuke meant that they needed a way to launch it. Launching a nuke, delivering a nuclear weapon to a target, and testing it require a separate set of technologies from the bomb physics. Early wartime delivery used heavy bombers to carry gravity bombs, with the Enola Gay and Bockscar being historical examples. Over time, missiles became the dominant delivery option because they can travel far and be launched with little warning. Ballistic missiles launch on a high arc trajectory, travel through space, and re-enter the atmosphere to deliver warheads across continents. Intercontinental ballistic missiles placed in hardened silos give a nation the ability to strike distant targets from home territory. Aside from that, submarine-launched ballistic missiles provide stealth and survivability by hiding launches under the sea, and cruise missiles carry nuclear warheads on jet-like flight paths and are harder to detect due to low-altitude flight. For this reason, aircraft, missiles, and submarines together form the triad many nuclear states use to ensure that a retaliatory capability survives an initial attack. Yet to be sure that they will work in battle, these killing machines must be tested. Testing of these weapons historically took place at dedicated sites where devices were detonated above ground, underground, or underwater to study blast effects and yield. Atmospheric testing was common in the 1940s through the 1960s, until concerns about fallout led to test ban treaties and a shift toward underground tests. These test programs measure blast overpressure, thermal radiation, prompt ionizing radiation, and longer-term radioactive contamination. As much as these tests are done, they all have one thing in common. The effects of a nuclear explosion are layered. There is the immediate thermal pulse that can ignite fuels and cause severe burns at large distances. And there is the shockwave that crushes buildings and sends lethal flying debris. But the silent killer of them all is the prompt radiation that can cause acute radiation sickness within a relatively short radius of the blast. Beyond the immediate area, radioactive fallout deposits particles of fission products and activated material over a wide region, depending on wind and weather. This fallout contaminates food and water, increases cancer risk, and renders areas hazardous to inhabit for years to decades in some cases. The profile of casualty types shifts with distance from ground zero. The closest zones face vaporization, the next rings face lethal burns and blast injuries, and the farther rings suffer survivable wounds compounded by radiation exposure and infrastructure collapse. Long-term health consequences include increased incidence of cancers. Genetic damage across generations is possible, though complex to measure. Psychological and social damage is also profound. Entire communities can be displaced, agricultural systems disrupted, and economies devastated. When many weapons are detonated in a regional or global exchange, scientists warn of climatic effects as soot and dust lofted into the stratosphere could lower sunlight reaching the surface, cooling global temperatures and reducing crop yields for years, a scenario often called nuclear winter. That outcome would magnify the human toll far beyond the immediate blast zones.